All right, we're going to talk about inverse and data assimilation problems for mining waste piles. These are Mark Stas's notes, the professor from the Applied Math Department at the University of Waterloo. I am currently working for him as a postdoc. My name is Justin Shaw, and I will be presenting. So, these mining rock piles are large, heterogeneous, and chemically complex, right? So, they're very large. You can see the scale of them here. This is supposed to be a dump truck. And they have a variety of sizes, and there's a lot of chemical processes. Sorry, a variety of sizes of the material that are deposited in them, even for a single pile. And there's a lot of chemical processes going on. It can be pretty harsh environments we're talking about, and so permeability is poorly constrained. We're not, we would like to find the permeability if possible, but we can't measure it directly generally. So we want to use simple mathematical, mathematical models to look at parameter characterization and possibly data assimilation in a data-centric manner. So we're essentially going to look for permeability by looking at what we do have, which is pressure data. So if I take a simple 1D model, which is what's written in red down here, with a possible extension to Klinkenberg effects right here, we're not going to worry too much about that today. But let's say we have two layers of constant permeability. So if we look at a two-layer model, and we have these two different kappas, so the different kappas are permeability, and we assume measurement locations at several places like this with the stars here. And if we have both layers sampled, we're hoping that we can get excuse me, some good information on kappa. There's a lot of things you can do in the lab, but we're not going to be in the lab. So the main thing I want you to take away from this slide is that we have these two layers. They have different permeabilities, and then we have this Z naught, which is the location of the transition, right? The Z equals Z naught is the location of the interface. So we don't know that. We don't know the two values of kappa. Maybe we do know the forcing at the top, right? Maybe from wind, something like that. This is we're going to do spectral methods is the main main takeaway from this, and we're gonna look at a non-dimensionalized version. So this is all just to basically set up the problem. I have two layers. Each of those layers has a specific permeability kappa. I have a Z naught. Neither of the permeabilities or the Z naught are known ahead of time. And so we're going to use an ensemble code, which I'll show in a separate video, to try a bunch of different two-layer setups and measure the pressure that we have against the pressure that results from those assumptions on the two-layer setup, right? So we can't measure the kappa directly. We don't know any of this, but we do know the pressure at these green star locations. And so we're going to try a bunch of Z naughts and delta kappas. That's going to be our parameter spaces, two-dimensional parameter space. The difference between these kappas and the location of the Z naught are the two parameters we're considering. And we're going to explore that parameter space and find which point in that parameter space, which delta kappa and which Z naught, correspond to pressure results that are most similar to measured pressure. Okay, so we're going to compute an ensemble of P for various KY, which is the distribution after you after you non-dimensionalize, right? So we'll just say this. We're going to compute an ensemble of P for various or non-dimensional P for various non-dimensional kappa of Z, and we measure the true P at a number of Z, and we're going to estimate the true value of that kappa distribution. Okay, and we're going to do it with built-in MATLAB stuff. Anyway, there's some non-dimensionalization here going on, but again, we've set up the problem now. We're going to explore parameter space, simulate a bunch of pressures, and then test those simulated pressures against the measured pressures at different locations. So that is the setup of the problem.